Hello students, welcome back to another video. Today's video will be doing paper 4 of course code 0625 February-March year 2024 variant 2. Question number 1 is saying figure 1.1 is a speed time graph for 5 minutes of a bus journey. Describe the motion between time 0.90 minutes to 2.9 minutes, then 2.9 minutes to 3.5 minutes, and 3.5 minutes to 4.5 minutes. So from 0.9 to 2.9, we can see it's a straight line. So if I see my velocity time graphs, when a line is straight, the velocity is constant and acceleration is 0. So I can say from here velocity is constant and acceleration is 0. From 2.9 to 3.5 it's a falling line, and velocity time graph of a falling line says that velocity is decreasing uniformly and acceleration is constant. So I'm writing over here. From 3.5 to 4 it's the velocity is 0, so that means the body would be at rest or the body would be stationary. So I'm writing rest. Writing all the information over here. B part says another bus travels at same speed of 8.9 meter per second. The brakes apply at constant force and the bus stop in a distance of 23 meter. The bus has the mass of 18,000 kilogram. So here we have a bus and the mass of the bus is 18,000 kilogram, and this bus is moving with velocity 8.9. Then we apply a force, or we apply the brakes to stop this bus, and then after traveling a distance of 23 meters the bus finally stops. So we are supposed to calculate the kinetic energy first. So kinetic energy is half mv squared. M is mass, which is 18,000, and V is velocity, which is 8.9. So I am taking square of it. So kinetic energy is 71000 joules. Second part says calculate the force applied to stop the ball, or we can say the force which these brakes are applying to stop this car. So we have multiple formulas to calculate force. I am not using the first one because I don't have acceleration, neither I can calculate it by any means, and I cannot use this formula because I don't have time. So I can use this middle formula because I have the energy, kinetic energy, and I have the distance as well. So change in energy is 710,000 joules and distance is 23. So the force is 30869 Newton. To 3 significant figure it would be 31,000 Newton. Second question says define impulse. So impulse is force multiplied by time for which the force acts, or we can say impulse is also equal to change in momentum of a body. B part says figure 2.1 shows a rocket and exhaust gases. So these are the exhaust gases that are coming out of a rocket, and due to these gases the rocket is moving forward to conserve the momentum. The exhaust gas are emitted from the rocket with velocity 1400 meter per second at the rate of 2800 kgs per second. Show that the force exerted on the rocket by exhaust gases are 3900 kilonewton. State the equation that you use. So we have the velocity of the rocket, which is 1400 meter per second, and the rate of ejection of gases is 2800 kg of gases are being emitted in a second. So we again have these three formulas. I can't use the second one because I don't have the energy, neither I have the distance, and I can use the third one because we don't have change in momentum as well. So we can calculate the acceleration and we can use the first formula. Now how we can get the acceleration? Acceleration is equals to change in velocity over time. And you know velocity change is 1400, and the time that we have is second because the rate is given us in second, so I can use the time as 1 second. So the acceleration is 1400. Now to get the force, I'll multiply the mass of the gas, which is 2800, with the acceleration, which is 1400, and the force is 392,000 Newton. To two significant figures it would be 3900 kilonewton. Second question says calculate the maximum mass that this force can lift from the ground, ignore the air resistance. So the weight that this rocket can bear is exactly equal to the upward force that is being applied by the gases. So the force that we have just calculated is 3900 kilonewton, and this is equals to the weight that can be lifted by this rocket. If this weight exceeds by this value, then the rocket won't be able to lift that weight. So maximum weight is equals to upward force. So weight is 3900,000 newton, and weight is equals to mass times gravitational acceleration, and mass is equals to weight divided by gravitational acceleration. So 3900,000 divided by 9.8. So maximum mass that can be bear by this rocket is 4 into 10 raised to power 5 kilogram. Third question says a car has weight of 13,000 Newton. The car is supported by 4 tires. The area of each tire in contact with the road is 0.016 meters square. Calculate the pressure on the road due to the weight of the car. So for example, this is the weight of the car, which is 1300 Newton, and each tire has a contact area of 0.016 meters square with the ground. And pressure is equals to force divided by area, or force per unit area. So force is equals to weight, and that is already given, which is 13,000 Newton. But about the area of contact of one tire is 0.016, and we have 4 tires, so I'll multiply the value by 4 to get the total area of 4 tires. So it would be 0.064 meters square. So I'm writing 0.064, and the final value for the pressure is 203.125 Pascal, and to two significant figure it would be 200 kilopascal. Second part says explain in terms of particle why the air pressure in the tire increases when the car travels along the road. The tire has air filled up in it, and when the tire roll over the ground, the friction between the ground and the tire produces temperature, and the temperature increases. Due to this increase in temperature, the kinetic energy of the molecule increases and they start moving faster. So friction between the road and the tire cause the temperature to increase. Air molecule in the tire gain more kinetic energy, move faster, and hit the walls of the container more frequently, causing pressure to increase. B part says a gas cylinder contains helium gas at pressure 2 into 10 raised to power 6 Pascal. A volume of 0.026 meter cube of compressed gas is released from the cylinder into the balloons. Each balloon contains 0.015 meter cube of helium at pressure 1 into 10 raised to power 5. The temperature remains constant. Calculate the maximum number of balloons that can be filled. So we have a container. The pressure of the container is 2 into 10 raised to power 6 Pascal, and the volume is 0.026 meter cube. And we are going to fill multiple balloons with this cylinder, and we are going to calculate the number of balloons that we can fill. Each balloon has the volume of 0.015 meter cube and the pressure of 1 into 10 raised to power 5 Pascal. I'm naming this as P1V1 and this as P2V2. I can use Boyle's law over here, which says that P1V1 is equals to P2V2. I'm multiplying it by n, which will represent the number of balloons that we can fill. So to get the n, I'll rearrange the equation. P1 is 2 into 10 raised to power 6. V1 is 0.026. P2 is 1 into 10 raised to power 5, and V2 is 0.015. Solving this into your calculator will give you 34.6 number of balloons, which is nearly equals to 35 number of balloons. Question number 4 says define specific heat capacity. It is energy required per unit mass per unit temperature increase. That means this is the amount of energy we need for 1 kg of mass to raise its temperature by 1 Celsius. B part says a volume of 0.0024 meter cube of oil is heated in a pan for 7 minutes. The temperature of the oil increases from 20 degrees Celsius to 180 degrees Celsius. The density of the oil is 910 and the specific heat capacity of the oil is 2000. Calculate the mass of the oil in the pan. So we are provided with volume and the time and the specific heat capacity, the change in temperature and the density. So I can use the formula of density to calculate the mass, which is density is equals to mass per unit volume. To get the mass, I can use density multiplied with volume. As the density is given, which is 910, volume is also given, which is 0.0024. Multiplying these both, the mass would be 2.2 kg. Second part says calculate the energy required to increase the temperature of the oil. As in question, the specific heat is given, so I can use the formula of specific heat energy and I will rearrange my formula with respect to energy. So it would be specific heat times mass times change in temperature. Specific heat is 2000. Mass that we have just calculated is 2.2 and the change in temperature was the temperature was going to increase from 20 degrees Celsius to 180 degrees Celsius. So overall increase in temperature or the change in temperature is 160. So I'm going to multiply it with 160. So the final energy is 700,000 joules. Third part says calculate the power required to supply the energy that we have just calculated. So, power is defined as energy supplied per unit time. So, we have the energy, we have the time. Now time is given in minutes, so we have to just convert our time into seconds and I'll multiply my time with 60 to get my times in seconds. 7 minutes would be equals to 420 seconds, so I'm putting 420. So the power would ultimately be equals to 166.6 watts. To two significant figures, it would be 700 watts. Fifth question says table 5.1 shows applications of region of electromagnetic spectrum. Complete the second column of the table with the region of electromagnetic spectrum used for each application. Choose from the region in the list. So we are provided with some region of electromagnetic spectrum. So for Bluetooth, we can use radio waves. For optical fiber, we can use infrared rays, security marking, UV rays, sterilization, gamma rays. Wireless internet, we can use microwave. Second part says state the approximate speed of radio waves in air. All the electromagnetic rays has the same speed in air, which is 3 into 10 raised to power 8 meter per second. B part says figure 5.1 shows successive crest of wave after a plane wave have passed through a gap. On figure 5.1, draw 3 successive crust before the wave reaches the gap. So in diffraction, if we have same medium over both sides, the wavelength remains same. So we have the same medium. So I'm measuring the wavelength after diffraction and the wavelength before diffraction would be exactly the same as after because there is no change in the medium. So I'm drawing the plane waves or crust of same wavelength. Wavelength of crust before diffraction is equals to wavelength of crust after diffraction. Second question says figure 5.2 shows a much wider gap. A plane wave of same wavelength is incident on the gap from left side of the barrier. So the incident ray has the same wavelength before, which was nearly equal to 1.3 centimeter for me. And the gap is much wider than 1.3. I'm writing few notes that if wavelength is equal to gap or wavelength is greater than the gap, then the diffraction would be more and the spreading would be more. But if the wavelength is much smaller than the gap, then there would be very less diffraction or very less spreading of waves. Our incident wave have the wavelength of nearly 1.3 centimeter and the gap is very much wider than 1.3, so the diffraction pattern will look like this, but the wavelength before diffraction and after diffraction is same as the medium is not changed. Thanks for watching the video. If you like the video, please hit the like button and subscribe my channel.